So welcome everyone to this fourth lecture of Engineering Thermodynamics. Myself Varad Daoo. I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the previous class, we have seen about what is internal energy and how to quantify it, and how internal energy is a path function how internal energy is a state function as opposed to path function. Further, we have also studied in detail about heat and work, and we have also understood its difference and similarity between both of those things. That is, both of them are path functions. And at the end, we have also studied about various processes such as adiabatic process or isothermal process, non-adiabatic process, reversible process, so on and so forth. So in the present class, we are going to take one step further, and we are going to study about a pressure volume work and the difference between reversible work and irreversible work. And then further, we are also going to quantify this pressure volume work in terms of volume and pressure of the system. Okay, so let us start thermodynamics. So the first topic which we are going to study is pressure volume work. Pressure volume work. Okay, so pressure volume work is the work done when the gas expands or contracts against the external pressure, which is usually the atmospheric pressure, right? Let us write this down. So pressure volume work is the work done when the gas expands or contracts against an external pressure. Now this pressure can be anything, but in usually we consider this pressure is atmospheric pressure. Usually atmospheric pressure, right? So in order to understand this, let me draw a figure. Okay. Consider this is cylinder. This is also a cylinder. Okay, so here what we have is, let us consider that there is some gas inside this. Okay, now let us consider that this was an initial state, and this is a B, which is final state. Okay, so let's consider its pressure is P and initial volume is Vi, right? And this is a piston, so there is a piston here. Okay, now this piston, what is it doing? It is applying an external pressure, right? This is P external, and it is applied in this direction. Okay, and let's consider this is a cross-sectional area. Okay, and after let's say, for example, because of this external pressure, what happens is this volume of this volume of the gas decreases, right? So for example, it goes into this state because of the external pressure. Now the volume occupied by gas is Vf. which is less than Vi, right? Pressure is going to remain the same, right? So this is the going to be the new position of piston, right? So this is P external, right? And let's say for example this was the initial position, right? So this was the initial position. So from this position to this position it has traveled dl distance, right? And this is going to be nothing but cross sectional area, right? So let us understand this. To understand this, let us consider a cylinder filled with a frictionless and weightless piston. What we are assuming is that this piston, this is the piston, this is going to be weightless, okay, weightless and frictionless, okay, having a cross sectional area equal to A, right? So cross sectional area is going to be A, okay, cross sectional area is going to be A. So let us consider a mole of a gas of volume Vi, and the pressure of the gas is P. So pressure of the gas inside this volume is P, whereas P external is this, which has been exerted. Now if P external is greater than P, what is going to happen? The volume of the gas is going to get lesser, right? So volume is going to so gas is going to get compressed. Whereas if P is greater than P external, then the gas is going to expand. So in current case, what we are assuming is that P external is greater than P, because of which, therefore, gas compression occurs, right? Okay. So if external pressure P external is greater than P, then piston is moved downward till the pressure inside the system cylinder becomes equal to P external, right? As shown in this figure, right? Right? So let us try to write this down first. Okay. So to understand pressure volume work, consider a system, a cylinder. Consider a cylinder filled with frictionless, fitted with frictionless, and weightless piston having a surface area, having a cross sectional area of equal to A, equal to, let's say for example, A. Okay. Now the second point, let it contains a mole of gas, contains a mole of gas of volume Vi, and the pressure of the gas inside is P, and the pressure of the gas inside is P. Okay. Now let the external pressure acting on the piston be P external, okay, or PEX. Okay, and if the external pressure, if the external pressure, which is PEX, is slightly greater than P, is slightly greater than P, that is PX is greater than P, then the piston is moved downward till the pressure inside the cylinder becomes equal to, till the pressure inside the cylinder becomes equal to P external, right? P external as shown in figure, B above, right? So now let us move on to the next page. So now let this change be achieved. Let this change be achieved in a single step, and the final volume be VF, right? During compression, suppose the piston moves, a very small distance L, which is L, right, which is shown here. So this is the distance with which it moves. Okay, then the change in volume is given by, the change in volume is given by the following thing. That volume, for example, let us use a different color. So volume change, this is nothing but delta V is going to be nothing but L into A, right? Which implies delta V, which is VF minus VI, is going to be L into A. And then we know that pressure is nothing but force per unit area, which implies force is equals to pressure into area, right? Therefore force on the piston, that we call as F. So F is getting to be P external into A, correct? Now if W is the work done on the system, by movement of the piston, by movement of the system of the piston, then we can write work, which is nothing but W, which is nothing but force into displacement, is going to be P external multiplied by A, right, multiplied by displacement, which is going to be L, right, which is going to be P external or P external into A into L, right, which is going to be Px multiplied by negative of delta V, is minus P external into delta V, right. Hence we can write it down, W is nothing but minus P external into final volume minus initial volume, right. So let us call this equation as equation number 1, right. But it may be noted that the negative sign of this expression, the negative sign of equation 1 is necessary to give the conventional sign for W, right. It is positive for compression as work done on the system, and hence Vf minus Vi will be negative, so that the negative multiplied by negative will be positive. However, if the external pressure is slightly less than the pressure of the gas, that is P external is less than P, the gas will expand, that is the work done will be by the system on the surrounding. In that case, Vf is going to be more than Vi, and hence delta V is going to be positive, and therefore W, that is work done, it will be negative as per our convention, right. So let us write this down. So work done is positive for compression as work is done on the system, right. So here Vf minus Vi, which is going to be nothing but delta V, will be negative, so that negative multiplied by negative will be positive, right. However, if the external pressure is slightly less than the pressure of the gas, that is Px is less than P, the gas will expand, right? That is what is going to happen is the work will be done by the system. The work will be done by the system on the surroundings. Right? So in that case, Vf will be more than Vi, right? And delta V will be positive, and therefore W will be negative as per convention. That is, W is going to be minus P external into delta V is going to be negative. Obviously, if there is no volume change, that is, if delta V is equal to 0, then no work is done no work is done by the system, right? So obviously, if there is no change in volume, that is, if delta V is going to be 0, then no work is done by the system, or on the system. That is, in that case, where W is going to be equal to 0. Alternatively, if the system is at lower pressure, the piston will be pushed down until the pressure of the system becomes equal to the surrounding. In this case, work is done on the system by the surrounding. In this way, energy transfer takes place from the system to the surrounding as work. If the system loses energy, we say that the work is done by the system. Alternatively, if the system gains the energy, then we say that work is done on the system, right? Let us write this down with a different color. So alternatively, if the system is at lower pressure, if the system is at lower pressure, then piston will be pushed down until the pressure of the system becomes equal to that of surroundings. In this case, work is done on the system. Work is done on the system by the surroundings. Right? In this way, energy transfer takes place. Energy transfer takes place from the system to the surrounding as work. From the system to the surroundings as work, right? Now if the system loses energy, we say that work is done. Work is done by the system. Alternatively, if the system gains energy, we say that work is done on the system. Work is done on the system, right? So thus, number one, if the gas expands, that is Vf is greater than Vi, and work is done by the system, then W is negative, right? Whereas if the gas contracts, that is Vf is less than Vi, and work is done on the system, then we have W is positive, right? So this is very important thing which you have to remember, right? Very important. Okay, so now let us move on. Now let us suppose that the pressure is not constant. So let me write this down with a different color. So in the previous case we have considered that the change in volume occurs in a single step and that the P external is going to be remain constant. Now let us consider that this P external is also not constant but is varying. So in that case what is going to be the pressure volume work? So now let us suppose that pressure is not constant, right? Not constant at every stage of compression, but changes in a number of finite steps, right? Then in that case, in this case work done on the gas will be summed, will be what? It will be summation of all the, will be summed over all the pressures, right? Summed over all the steps and will be equal to what? It will be equal to W is equals to minus summation over all pressures, right? P external multiplied by delta V, right? So this can be understood from this figure. Okay, this can be understood from this figure, from this 8A, right, from this figure. So what we have, if the pressure is not constant but changes in an infinite number of steps such that it is always infinitesimally greater than the pressure of the gas, that is this is there is another terminology for this. This is called as reversible work done, right? So this is a reversible work done in which each step is in equilibrium, whereas right, so this is a reversible in which each step is an equilibrium, right? So whereas here the pressure is going to remain the constant, each step is not in equilibrium, right? So this is an irreversible work. Definition of irreversible work, where this is a reversible work, right? So if the pressure is not constant but changes in an infinite number of steps such that it is always infinitesimally greater than the pressure of the gas, then then this is called as reversible conditions. So let at each step, so let us write this down, let us derive an expression for this. So if the pressure is not constant, if the pressure is not constant but changes in an infinite number of steps such that it is always infinitesimally greater than the pressure of the gas, than the pressure of the gas. This is called as a reversible conditions. So let at each stage the piston moves in an infinitesimally small distance dl. Then infinitesimally small decrease in volume is dV, right? And given by dV is equal to nothing but change in cross sectional area multiplied by change in length. Therefore force is nothing but F is nothing but, we have seen that it is going to be P external multiplied by A. Therefore work is going to be nothing but force into area, which is P external, force into distance, displacement, basically into displacement. This is nothing but P external into A into dl, right? But what is ADL? ADL is nothing but change in volume, P external into dV, right? This is nothing but dW. Now if the volume of the system changes by a finite quantity Vi to Vf, let us now if the volume of the system changes by a finite quantity from volume Vi to Vf, right? Then the total work done, then the total work done on the system, which can be represented as W, can be obtained by integrating P external into dV when P is constant, right, over the volume, entire volume change, over the volume change from Vi to Vf. Therefore, we know that dW is nothing but P external into dV. Therefore, W is nothing but integral dW, which is integral P external into dV when V is equals to Vi to V is equals to Vf. Right, now if P external is going to constant, then we can say that W is nothing but integral dW, which is going to be P external into integral V dV Vi to Vf. This is nothing but P external into Vf minus Vi, right? It may be noted that in above expression, P external at each stage is equal to P in plus P dP. Let me write this down. So, it may be noted that in above expression, Pex at each stage is equal to P in plus dP in case of compression, right? Similarly, in an expansion process, under similar condition, the external pressure is always less than the pressure of the system. That is, P external in that case will be P in minus P dP, right? So, in general, we may write P external is nothing but P internal plus minus dP, right? And such processes are called as reversible processes. So, thus we can write, thus a process or change is said to be reversible if it is brought out brought out in such a way that the process could at any moment not movement, it is at any moment be reversed by an infinitesimal change, right? A reversible process proceeds infinitesimally slowly by a series of equilibrium states such that the system and the surroundings are always in near equilibrium with each other. And the processes which are not reversible are called as irreversible processes, right? So in this current class we have seen about pressure volume work, and then we have also seen how to help to quantify this pressure volume work both in terms of reversible as well as in irreversible case. So in the next class we are going to continue this calculation of work for different processes such as an isothermal or isobaric or isoconic processes, so on and so forth. And we will also further we will also see a special case of expansion, which is free expansion, in which the pressure volume work is going to be 0. And then if the time permits, we will also delve deeper into law of conservation of energy, which is nothing but the first law of thermodynamics. Okay, so I thank you all for attending this class, and I hope to see you all again in the next class. Thank you.